Okay, in this session we are going to be talking about some basic chemical symbols of some elements and compounds, the way they are written. This will actually prepare us into the calculation aspect or the stoichiometric aspects of chemistry. So we are going to have a heading: chemical symbols of elements. In chemistry, Berzelius in 1814 contributed that it is more easier and less cumbersome to represent elements in a coded form. Yeah, I said coded form because there should be a simpler way of representing the elements, because you have over 106 elements in the periodic table. So for the purposes of reactions, calculations, and wanting to represent those elements in more simpler form, he suggested that it is better that every element has its own unique way of representation, so that it will be less easier for us. So for example, most time you can have a very long name and then you hear AKA that. So you see, you always have an AKA that is simpler and in a shorter form compared to your very own long name. So you see some people having very long names, and then some people prefer calling the shorter form of their name to make it less cumbersome for them or easier for them. So he talked about making sure that elements are represented with symbols, and in chemistry today it becomes easier for us calculating or representing these elements in reactions, because someone else reasoned and did a whole lot of work to make sure that these elements are coded in an easier way. So we have, like I said, over 106 elements. Now, there are different ways these elements are represented. One of the ways it is represented is, it can either be the combination of the first letter found in the name of that element and another letter to form the symbol for that element, or it can be the first letter of that element. So for example, we have phosphorus has a symbol P. We have nitrogen having the symbol N. We have oxygen having the symbol O. So these are ways these elements are represented. Now, like I said, in another form, there is a pattern in representing elements in which the first letter that is found in their name is combined with another letter, and then it forms the symbol for that element. So wherever we have, for the first scenario, wherever we have phosphorus, instead of writing phosphorus as long as the name is, we can just represent it by a P, and then a good chemist will say, oh, this is phosphorus. So now the second way I told you was a combination. So we have, for example, chlorine. We have now chlorine is a combination of C and L. And then we have cobalt. Cobalt is a combination of C and O. We have argentum. It's a combination of A and G. We have zirconium, Z and R. So these names are now derived by a combination of the first letter and another letter. So you can see that chlorine is a combination of C and L. Cobalt is a combination of C and O. Argentum is a combination of A and G. Zirconium is a combination of Z and R. So this is another method in which you represent these elements. Now, another classical way of representing these elements, as he said, is using their Latin nomenclatures. So every element has a Latin name. A classical example is our sodium. So you see, you have elements like sulfur. So sulfur already has S as its symbol. So sodium is S2. And probably by the time you use S for sodium, it will be contradictory because you have two elements bearing the same symbol. So sodium now takes its Latin name, which is natrium. So you see sodium, the Latin name natrium is used, and then N in combination with A is now the symbol of sodium. So wherever you see sodium, you see Na. So that's a classical example. Another example is copper. Copper is cuprum. Cuprum is Cu. So you have cuprum as copper. Another is our gold. Gold is aurum. Aurum is Au. So these are classical examples in which, or classical ways in which you represent these elements. Now, like I told you, the major reasons for this is because we must have a very classified way. For example, you cannot actually be representing the names of these elements as they seem in a chemical equation. It will be too cumbersome, and of course that reaction, most times you want to draw a very lengthy reaction, it will be very frustrating and difficult. So these ways we are brought in to make sure that it makes things easier for us. Now, another concept I will talk about is the atomicity of elements. Now, atomicity of elements is very important because these are the ways they are represented in chemical equations. So if we miss it now, like I told you, we are going into the calculation aspect of chemistry, and we must understand how compounds are written, how molecules are written, in order for us to work with them, because there is a point we get to, we'll need to be calculating the reacting mass, we'll need to be calculating the molecular mass. Hey, don't be in a hurry, don't fidget. We will get there and I will explain every bit of what I'm saying to you. So I'm just citing an example for us, and I'm telling us the reason why I'm having this class as a foundation class. So when we have the foundation right, we can actually build mansions. So for us to build mansions in chemistry, we must get the foundation right. So that is why I'm taking my time to take this class with us. Alright, so like I said, the atomicity of elements is very important. You know, some atoms are monoatomic, some atoms are diatomic, some atoms are triatomic. Well, we have atoms that contains 4 molecules. We can call them tetraatomic, but they are mostly non-existent, so we don't actually consider them. So now, so you have monoatomic, You have diatomic. You have triatomic. For the purpose of this class, there is only one element that is actually triatomic, and that's ozone. So when you see ozone, ozone is triatomic, but we'll get there. Now, we have elements that are monatomic. Monatomic elements, we have carbon, represented as C. We have boron, represented as B. We have barium as Ba. Now, when I mean by monoatomic, I don't want you to get it twisted. I'm not talking of the letters found in that symbol. That's not the atomicity. The atomicity describes the number of that particular element that can exist independently. So when I'm saying barium, barium is Ba. So you shouldn't see it and say, how is it monatomic when you're having Ba? Ba is just a symbol, and I've been able to deal with symbols of elements before coming to this. So we have monatoms or monatomic elements, and I've been able to name some. So we have barium, like I said. We have copper. Of course, copper, like I told us, is represented as Cu. Now, these are monatomic elements. You have diatomic elements. Now, diatomic elements, you have basically the gases. Yeah, the gases actually basically exist as diatomic elements. So you see most of the elements I'm going to be naming here are mostly gases. So they exist in twos. So you always see them having a subscript 2. So we have chlorine, that's chlorine. You have hydrogen. Of course, hydrogen is in group 1, it's grouped alongside the alkali metals. Like I said, when I use high sounding word, I don't want you to fidget. When we get to periodic table, you get to know what alkali metals. They are group 1 elements. You know their characteristics. And so it's among the alkalis. It's placed there for convenience, but it's not actually a statutory member of the alkali metal. So hydrogen is a non-metal. I should sound this again. Hydrogen is a non-metal. That you see it among metals does not make it a metal. So it comes out as a diatom. You see the other members of group 1 are monatomic elements. It's a diatom. So you see hydrogen is giving us H2. You have nitrogen. Nitrogen is giving us N2. You have, we consider fluorine. Like I've said, this is chlorine. Chlorine is actually in the same group with fluorine. So, but let's just, for emphasis purpose, you have fluorine. Fluorine also, it's a diatom, and it goes on and on. So these are some of the diatoms you have. Then you have triatoms. Like I said, under triatoms, you only have one royal majesty occupying there, and that's ozone. So ozone is giving us O3. That's ozone. So there is no other triatom that's in existence in chemistry I know of. It's ozone that is actually the triatom that is actually known. And then we said that tetraatoms, atoms with 4 atoms, or elements with 4 atoms are non-existent. So we've said that already. So now this is what we call atomicity in chemistry. Now, in writing the formulas of compounds, you see that it is very necessary to put this atomicity in mind. So you see the formulas of some compounds are a combination of molecules. So you see molecules coming together or elements coming together in a close proximity and with their subscripts to form compounds. So for example, you have hydrochloric acid. Now, hydrochloric acid is a compound, and you can see that it's a combination of, you see hydro and chloric. So it's a combination of hydrogen and chlorine. So you see hydrogen and chlorine coming together. So we don't write them by putting a space in between them. They come so close, there is no space. So you see HCl, that's a compound. It's a combination of an atom of hydrogen and an atom of chlorine. Another example is our sulfuric acid, what it's known as tetraoxosulfate 6 acid. That is the IUPAC nomenclature. The sulfuric acid is the old name. So tetraoxosulfate 6 acid is given as H2SO4. So you can see you are having H subscript 2. That's telling you that it's a molecule of chlorine that is there. And then you have 1 atom of sulfur, and then you can have 4 atoms of oxygen making this compound. You have many other compounds. You have lead nitrate. Now this is the old name. The IUPAC nomenclature of this compound is lead 2 trioxonitrate 5, lead 2 trioxonitrate 5, and then you now have calcium carbonate. Calcium carbonate is CaHCO3 and then 2. So that's calcium carbonate. Calcium carbonate. The IUPAC nomenclature is actually, so it is calcium bicarbonate. The IUPAC nomenclature is calcium tetraoxo 4 bicarbonate. Calcium trioxo 4 bicarbonate. That's it. So that's the IUPAC nomenclature. That's the IUPAC nomenclature. So you have calcium carbonate written as this. Then let's take one more example. You have potassium sulfate. Potassium sulfate given as K2SO4. So this is potassium tetraoxosulfate 6. It's actually a salt. So that is the way compounds are represented. So now, having known this, I believe this will give us a background and a good foundation to launch into the calculation aspects of chemistry, also most times called stoichiometry. I wouldn't want you to miss that class, because my next classes will be the most exciting and educating classes.